So today we have Jack Davies speaking on TMF, or How I Learned to Stop Worrying and Love Spectral Algebraic Geometry.
Well, thank you, Sarah, for getting through the title for me. Yeah, and thank you all for coming here. So yeah, as the title indicates, I would like to talk about TMF, and I would like to talk about it through the language of spectral algebraic geometry. My goal is to give you some sort of motivation and a bit of intuition behind what's going on. I don't really want to get into super detailed proofs and technical statements or stuff like this. I'm going to have a list of references at the end so you can find all the good details there. But today what I'm really interested in is, let's make sure my PDF thing works. Oh yeah, nice. I just want to talk about some things from algebraic geometry and topology. So I just want to introduce some basic characters that we're going to see. I then want to involve these characters inside some statements and theorems, which will then not only motivate, but eventually give us a definition of TMF. And I'll talk about TMF for just a little bit and why it might be useful and why it's interesting and why we might naturally come up with this definition. Then I'd like to talk about a sort of spectral algebrogeometric point of view of TMF. So we'll take a total right turn and a totally different point of view. But I hope sort of like the intuition and motivation that we've built up earlier on will carry over into the spectral world. And lastly, depending on time and stuff like that, I've got a few examples of other things we can do with spectral algebraic geometry if we continue down this similar path of this spectral algebrogeometric version of TMF. I also told myself that because it's an online talk, I will take drinks of water sort of periodically so that you're not just hearing my voice the whole time, and also maybe give some space for questions, but feel free to ask questions at any time too. So to get started, I want to talk about generalized cohomology theories. So they're sort of the basics of algebraic topology, but as modern homotopy theorists, we're interested in not really the cohomology theories, but the spectra which represent them. So some examples of these things are like rational singular cohomology, topological K-theory, and complex cobordism. And I listed the notation for the spectra there on the right. And of course, there are many, many more examples. But some of the motivation behind TMF is a new type of cohomology theory called elliptic cohomology theories. You should think about them, if you imagine the list I gave you above of those three things as being some sort of hierarchy, then elliptic cohomology theories fit somewhere in between topological K-theory and complex cobordism. They're a little more complicated than topological K-theory, but they're still somehow more simple than studying the homotopy groups of spheres. So let's talk about some elliptic cohomology theories. The word elliptic comes from elliptic curves. And elliptic curves, I'm not going to give you a real definition for them, but they're just nice algebrogeometric objects. So they're a type of smooth curve, so some nice curve with coefficients in some ring or some field. And they're smooth, so there's no singularities or anything like that. And what makes them so interesting is that they have a natural group structure. And it's this group structure that is somehow mysterious and rich and full of information. So I give you an example of an elliptic curve so you can be convinced that you can just write them down on a piece of paper. It's quite nice. I hope it's an elliptic curve. I didn't compute its discriminant. So elliptic curves are really cool because they pop up all over mathematics. I mean, you can study them using complex analysis and number theory, and they also pop up in algebraic geometry, arithmetic geometry, and topology. And today we'll sort of see how they affect homotopy theory. To give us the language to talk about elliptic cohomology theories, though, and going forward into spectral algebraic geometry eventually, I'm going to have to talk about just algebraic geometry for a little while. And the point of view I'm going to take to study algebraic geometry is called the functorial approach. So I hope a few of us have seen the basics of algebraic geometry before, just the super basics, the definition of a scheme. So basic algebraic geometry is about studying, you have commutative rings and algebraic things on the left, and on the right you have these geometric objects, these affine schemes. And basic algebraic geometry tells you that these two things are the same. You can study commutative rings or you can study affine algebraic geometry. And the equivalence of categories there is given by sending a ring to its Zariski spectrum, spec of R. Now, one thing you might want to do, and quite a trivial remark, is the existence of the Oneida lemma. So the Oneida lemma tells us that if you want to study affine algebraic geometry, then since the Oneida lemma gives us a fully faithful embedding into this functor category, so functors from commutative rings to spaces, the Oneida lemma tells us that we can study this functor category on the right, and we're going to be able to make a lot of the statements that we make in affine algebraic geometry inside this functor category. Just as a side note, if I was making this talk to algebraic geometers, then I wouldn't put the category of spaces there. I would put the category of sets, and we would work one categorically and maybe two categorically at some stage. But since we're homotopy theorists and we're topologists and stuff like that, I'm going to work infinity categorically. And so everything I've got on the board is going to be in terms of infinity categories. So there's still lots of one categories going around, but you should think we're not just looking at functors from commutative rings to sets, but we're actually looking at potentially interesting functors from commutative rings to spaces. Okay, that's just a side note. So now you can actually do a little bit more because the category of affine schemes obviously lives inside the category of schemes. And this is what algebraic geometry is all about. It's about studying this category of schemes. And there's a functor which goes from the category of schemes that's exactly a Oneida embedding. It's exactly there's a functor that goes from the category of schemes to this functor category, which sends a scheme X to the functor that represents X. So in other words, it sends X to H of X, and H of X is given by that formula that I've got on the board, or on the slides rather. Now what's cool, and what you find out doing the foundations of algebraic geometry, is that this functor, which sends a scheme X to its the functor representing X, is also a fully faithful embedding. And this essentially is a consequence of the fact that schemes themselves are covered by affine schemes. So the point of making this statement is that if you want to study algebraic geometry, you don't necessarily have to study the category of schemes and look at locally ringed spaces and maps between them and think about sheaves and stuff. You can think about this functor category, and you'll be able to make all your algebrogeometric statements inside this functor category. If you choose to study algebraic geometry through the lens of this category, then it's called taking the functor of points perspective. That's going to be powerful for us because we're going to want to talk about more complicated things than schemes, and we're also going to want to talk about spectral algebraic geometry at some stage, and I find this point of view generalizes in a very natural way. Okay, so we're going to want to study this functor category. So I'm going to name objects of this functor category. I'm going to be calling them pre-stacks. So a pre-stack is simply a functor from commutative rings to spaces. I can give you some examples. What's the point of, I think a theme throughout this talk and a lot of mathematical talks is what's the point of complications and generalizations if you don't have examples? And hopefully I give you an example at every moment. So yeah, what is an example of a pre-stack? Well, the representable functor I gave you before. This is a little bit trivial, but it's a very important example. So if you have a fixed scheme X, there's a functor which sends R to, this representable guy. The thing that's uninteresting about this example is that it's very one categorical in the sense that these mapping spaces are actually discrete. So they're homotopy equivalent to a mapping set. So we're not really making use of any of the higher homotopy groups that we have available since we're looking at functors going into spaces. But we can very easily construct examples that do land in spaces and not just discrete spaces. For example, you could send a ring R to the classifying space of its group of units. Albeit this doesn't have very many higher homotopy groups, but it is not just a set.
Jack, could you explain like what's the higher, like, you know, how is commutative rings like an infinity category? Oh,
good question. So I'm just taking the nerve of commutative rings. So a functor from commutative rings to spaces, I'm thinking of as it's really an assignment of a ring to a space and a map of rings to a map of spaces, but these still need to satisfy the higher homotopy coherences inside the infinity category of spaces. But yeah, I'm just thinking about this as the nerve of commutative rings. Good question. So there's also more complicated examples. For example, you could send a ring R to its algebraic K-theory. I mean, this might have infinitely many higher homotopy groups. The example we're going to be most interested in, though, and this is where the word elliptic pops up again, is we're going to be interested in this functor, which sends a ring R to the groupoid of elliptic curves over spec of R. So I haven't told you what an elliptic curve is yet, and I don't plan on it. But remember that it's some sort of smooth curve with a natural group structure that's somehow so beautiful that it's worthy of study. And when I say an elliptic curve is over a ring R, it means it just has coefficients in this ring R. Or if it's over a scheme X, it means that it is built up from the local affine charts of that scheme. So what is the groupoid of elliptic curves over a fixed ring R? Well, you just look at the category of elliptic curves, which you can define if someone gives you a definition of an elliptic curve, and you just take the groupoid of this category. So you throw away all the non-invertible morphisms. So like I said, this is a functor that we're going to be very interested in. This is our pre-stack of interest, something I'd like you to remember throughout the talk. And I'm going to denote it by ML, and I'm going to call it the moduli stack of elliptic curves. Just a quick note, since we're considering the category of schemes as being embedded into this functor category, we're not differentiating between a scheme and the functor that represents that scheme. So in particular, a map from a scheme to this moduli stack of elliptic curves is just a natural transformation from the functor representing X into the moduli stack of elliptic curves. And the Oneida lemma just immediately tells us that such a map is defined by just choosing an elliptic curve over this scheme X. So this will come up quite a lot. Every time I construct a map from a scheme into the moduli stack of elliptic curves, I'm just going to choose an elliptic curve over X. It's I'm not going to do anything more than that. Okay, so yeah, these are some examples of some pre-stacks, but I've already used the word stack, so I should probably give this at least a loose definition. A stack for us is just going to be an infinity categorical sheaf. So let me say a few words about this, but this is not really the point of the talk, so I don't really want to go into too many details. Oh, excuse me. So by an infinity categorical sheaf, I mean a sheaf is something where global sections are defined by a collection of local sections which agree on intersections. But since we're working with higher categories, I ask that so an infinity categorical sheaf is going to be one where global sections are defined by a collection of local sections, but these don't necessarily agree on the intersections, but there is a homotopy between these local sections on their double intersections. So you have a collection of homotopies now, more information. And moreover, you continue and you ask that these homotopies are connected by higher homotopies on the triple intersections, and these on quadruple intersections, we have even higher homotopies, and et cetera, et cetera. If you look at some paper, if you look at higher topos theory, there's a definition in there. It might be a little bit opaque, but if you read some papers on derived algebraic geometry by Tuen, he talks about these sorts of things in a little bit more detail. Okay, anyway, the important definition on this slide is not the definition of a stack, but rather the next definition. And it's going to be prefaced by a piece of motivation or an example. So we say that so what is the definition of a scheme? It's a locally ringed space which has an open cover by affine schemes. Another way to phrase this is a scheme is exactly a stack which has an open cover by affine schemes. So I'm going to define a Deligne-Mumford stack to be a stack which has an étale cover by affine schemes. Now, I don't really want to get into the definition of étale, and don't worry, there will be definitions and stuff coming up, so don't worry about that. But you should think about an étale map as being a sort of like a covering space map. So in particular, what is an open cover of a space? Well, you choose a whole bunch of open subsets, let's say a whole bunch of open immersions, such that the union of all of these open immersions gives you your whole space. So what is an étale cover? Well, you start with a space or some sort of stack, and you now have a whole bunch of locally étale maps. So you have a whole bunch of local covering spaces. And it's not necessarily true that one of these covering spaces covers your whole stack, but when you take the union of all these local covering spaces, you have a cover for your whole stack. So it will come up once or twice in this talk. And again, you're really free to ask me the sort of rhetorical question like, why do you define these things? And what's the point of working with generalizations and complications? But the excuse that I'll give again is because we have an example. The moduli stack of elliptic curves is in fact a Deligne-Mumford stack. It has a particular étale cover by affine schemes, and this étale cover cannot be rectified to an open cover or anything like this. This is the moduli stack of elliptic curves is truly a Deligne-Mumford stack. It's definitely not a scheme. Okay, so I now have another jarring change of pace for a second. The Landweber-Exact-Functor theorem. Where is this coming from? Well, there's a reason why I've been talking about stacks in this topology talk for like 10 minutes already. And the reason why is I want to state the Landweber-Exact-Functor theorem, which is going to be a famous theorem from the 80s, which constructs elliptic cohomology theories for us. And well, let me just state this theorem. So the Landweber-Exact-Functor theorem says, start with a ring R, doesn't matter what it is, any ring you like, and choose an elliptic curve over that ring. So in particular, it might be the example that you saw before. I'm not sure if that's a nice enough elliptic curve. So actually write this down. Now, since you have an elliptic curve over a ring R, by the Oneida lemma, as I mentioned before, you have a map from the spectrum of R into the moduli stack of elliptic curves. So the Landweber-Exact-Functor theorem now says that if you have this data and this map of stacks is flat, if you forget what the word flat means, it has something to do with the word exact in the Landweber-Exact-Functor theorem. So if we have this data, oh, sorry, and by the way, the adjective flat here is something that you can actually check. It's not some mystical statement that you need high-powered mathematics to prove. You can actually write down equations and check Jacobians and double check flatness and stuff like this. So given this information, an elliptic curve over a ring R such that the defining map into the moduli stack of elliptic curves is flat, then the Landweber-Exact-Functor theorem produces an elliptic cohomology theory for you. It says that there's some homotopy commutative ring spectrum, and you totally understand its homotopy groups. It says its homotopy groups are, there's no odd homotopy groups, and you have a copy of the ring R in degree 0, and in fact in every even degree. And the way to express this multiplicatively is to say that there's sort of a bot element adjoined to this ring. Well, so you should imagine the homotopy groups of this elliptic cohomology theory as behaving very much like complex K theory. Okay, so this is the relation between the elliptic cohomology theory and the ring R, but it also has a relation to the elliptic curve E, and that's sort of the interesting part, or else the theorem's not super exciting. And I'm not going to state it in a huge amount of detail, but essentially, you can locally construct the elliptic curve E by looking at the cohomology of CP infinity with respect to this elliptic cohomology theory. Now, when I say locally construct, I mean you should think about an elliptic curve as being somewhat reminiscent to a compact Lie group. And for a compact Lie group, you have a Lie algebra. And when I say locally construct, I mean you can use the cohomology of CP infinity to reconstruct the Lie algebra associated to this elliptic curve. Like I said, there'll be some references at the end for where you can find some slightly more precise statements. Okay, so I have a natural question when I see a theorem like this, and it is the following. If we have an elliptic curve E, over a scheme X. So this means that it's, a scheme is covered by affine schemes, a whole bunch of spec of Ri. And having an elliptic curve over a scheme means that you have an elliptic curve over each of these affine open covers, each of these elements in the affine cover, and which is an elliptic curve itself. And so you could ask yourself, well, can I run the above theorem to produce a whole bunch of elliptic cohomology theories for me, which defined locally on this affine cover, and then can I glue these elliptic cohomology theories together to obtain some sort of cohomology theory associated to the scheme X, not just associated to pieces of the open cover? In other words, we're kind of asking, can you apply the Landweber exact functor theorem in a kind of sheafy way?
Jack, is there like a easy kind of, so if it turns out like that the cohomology theory I get is like complex oriented, does that correspond to something about the elliptic curve?
Yeah. So when I say locally construct E from the cohomology of CP infinity, I exactly mean that there is an explicit complex orientation that's given to E, and you then use this to.
Okay.
And when I say locally construct the elliptic curve, I mean the formal group or the formal group law associated to that elliptic curve is then reconstructed in this way.
Okay, thanks.
Yeah. So if you know about complex oriented cohomology theories, this is all working in the background. Well, in the foreground, but I've just covered it up. So you can ask a question here. Can I glue together a whole bunch of elliptic cohomology theories to obtain one defined over a whole scheme rather than just on affine schemes?
So
and unfortunately,
do you mean anything more than, by locally construct, do you mean anything more than just that E naught of CP infinity is a formal neighborhood of elliptic curve?
I couldn't quite hear you, but I'm going to assume that you said, essentially, I just want to apply the Landweber exact functor theorem for every single time for each element in an open cover. Now, unfortunately, the answer is no. You cannot just glue elliptic cohomology theories together in a nice way. But the reason why you cannot do this is somewhat stupid. It's just because the stable homotopy category, it doesn't have very many limits and colimits. So notice that the Landweber exact functor theorem just gives you a homotopy commutative cohomology theory, but it doesn't say anything about higher multiplications or anything like this. And any of us who have worked with homotopy commutative ring spectra know that sort of their module categories are terrible and you cannot take limits and colimits and things are a bit of a nightmare. So what is the solution to this problem? How can we construct elliptic cohomology theories in a way that we can sort of glue them together? The answer is to use the Gauss-Hopkins-Miller theorem and to use infinity categories instead. So what does the Gauss-Hopkins-Miller theorem say? It says, well, start with the same setup. Start with an elliptic curve over a ring R, but don't just ask for this map now to be flat, but now ask for this map to be étale. So here's this word popping up again. So the one thing I want to say at the moment is that these restrictions, asking this map to be étale is very restrictive. It's much more restrictive than asking this map to be flat. Okay, but if this map now from spec of R to the moduli stack of elliptic curves is étale, then the Gauss-Hopkins-Miller theorem says that the cohomology theory you constructed using the Landweber exact functor theorem is actually E infinity. So it says that there is an E infinity elliptic cohomology theory, and it has the same properties as the cohomology theory that came from the Landweber exact functor theorem. It says that its homotopy groups, at least locally, sort of look like K theory, and that you can still construct your elliptic curve from this elliptic cohomology theory. Okay. Oh yeah, sorry. And moreover, and this is kind of the point of the previous slide, it says that this assignment, which sends an elliptic curve, which is étale over the moduli stack of elliptic curves to this E infinity elliptic cohomology theory, it says that this assignment is a sheaf. So it says that you can glue things together. And just as a side note, the original proof of this theorem essentially uses the Landweber exact functor theorem, and then you apply lots of difficult obstruction theory to obtain your E infinity guy. It's a very difficult proof. If I remember if I'm not misquoting Paul Gers, he said it was the hardest proof that he had to prove. It's not a very good sentence. Yeah. Are there any questions at the moment?
Can you just say again, what was this hard thing?
The hard thing is when you apply the Landweber exact functor theorem, you obtain a homotopy commutative ring spectrum. And this theorem says that you have this homotopy commutative multiplication, and this theorem says that you can sort of strictify this homotopy commutative multiplication to be an E infinity multiplication. So it says it kind of constructs, well, it doesn't construct anything. It uses obstruction theory to show that there's no obstruction to such a homotopy commutative guy being E infinity. So the problem is developing the obstruction theory and then also proving that the relevant obstruction groups vanish. Thanks. No problem. Okay, so let's play around for a little bit. We have this assignment. You might not have noticed, I can use my mouse here. I called this elliptic cohomology theory, I talked about this assignment OTOP. I talked about it here too. So that's what we're going to be interested in now. We're going to be playing around with this OTOP for a second. So we can do what I said we couldn't do with homotopy commutative ring spectra with E infinity ring spectra, essentially because they have all the limits and colimits that we desire. So we can glue together, if we have a scheme X and a whole bunch of elliptic curves defined over an affine cover, and we can feed it into the theorem, then we can glue together these elliptic cohomology theories to obtain some sort of a more universal elliptic cohomology theory. But actually there's even more that we can do, because this is not just a sheaf that sort of behaves well with respect to open covers, but it's an étale sheaf. So it means it behaves well with respect to étale covers. And what I mean by this is, say we have an étale map, not from a scheme now, but now from a Deligne-Mumford stack into the moduli stack of elliptic curves. Then we can define an elliptic cohomology theory, not just associated to the étale cover of this Deligne-Mumford stack by its affine schemes, but we can define an elliptic cohomology theory associated to this Deligne-Mumford stack. And I'll give you a terrible formula now, I think just because I typed it and I didn't want to delete it at some stage. But you can see this formula looks very much like if you cover up the third product sign with your hand, it's exactly an equalizer, which is exactly the sheaf condition that you normally see. It's just in the infinity categorical world, you need to continue off to the right infinitely. It's some sort of a cosimplicial object. We're taking some totalization. Okay, so again, you can ask me the question, like, why are we doing all of this, Jack? Because what's the point of constructing OTOP and saying that we can do all these nice things to Deligne-Mumford stacks if we only learned about these objects 10 minutes ago? But I claim that everyone that's watching actually knows an example of an étale morphism from a Deligne-Mumford stack into the moduli stack of elliptic curves. And yeah, I'm gonna be brave and wait for a suggestion. The identity. Nice. That was really fast. I love your enthusiasm. So the identity. So if the identity is not étale, then I don't know. Grothendieck is rolling in his grave. So the identity is étale, and the moduli stack of elliptic curves is a Deligne-Mumford stack, because that was one of the only things I told you before. Fantastic. So this is the definition of TMF. It's just you apply OTOP to the moduli stack of elliptic curves. So how should you sort of think about this? I mean, if the moduli stack of elliptic curves is some sort of stack that understands every elliptic curve over every ring, then TMF, or let's just say, yeah, TMF is essentially defined by taking some homotopy limit of all étale cohomology, elliptic cohomology theories, and gluing them all together in a coherent way. Of course, it's doing a lot more work than I give it credit for with this ridiculous formula that's on the slide now. But yes, this is the definition of TMF. Nice. And again, you can ask this question, like, I mean, who cares? I mean, so you define TMF, but what can we do with it? I claim that you can actually do a lot with it, mainly because it comes with a spectral sequence. So there's a spectral sequence that helps you compute the homotopy groups of TMF. All you have to do is understand enough algebraic geometry to compute the sheaf cohomology groups on the left. Now, I don't claim that I know how to do this off the top of my head at all, but there are some very nice expositions by Tilman Bauer and Akil Matthew and Lennart Meyer that explain that this spectral sequence is totally understood. There's no differentials that we do not understand. We know exactly what happens to the spectral sequence. So it means that we can compute the homotopy groups of TMF, and cool, now we can start playing with things. We've got a nice ring spectrum, somehow a universal elliptic cohomology theory, and we can see what we want to do with it.
Sorry. Can you see why? Oh, sorry. Go ahead.
This might be a stupid detail, but what does divided by 2 mean here? Like for S and integer?
Yeah, it's a bit weird. If it means that if S is odd, just everything's 0.
Okay.
Yeah, good question.
Can you see? Can you see why it's periodic? Like why the period is like 256 or whatever here?
Not from the spectral sequence, because the element that gives you the periodicity in the spectral sequence, at primes away from 2 and 3, it immediately gives you the periodicity, like the E2 page tells you the period. But at the primes 2 and 3, things get much more complicated, and yeah, you have to check some spectral sequence. Okay, so why the name? I mean, it's called topological modular forms. I would have called it like ultimate elliptic cohomology or something like this. But it's because this thing has been studied in mathematics before. So you've got a spectral sequence. It comes with an edge map that goes from the homotopy groups of TMF into these sheaf cohomology groups, or into these global sections of some sheaf that I haven't defined. And the object on the right is just called the ring of modular forms. And actually this map defines quite a lot of elements in the homotopy groups of TMF. We actually name a lot of elements in pi star, inside pi star of TMF by their names in the ring of modular forms on the right. I hope that my pointing is going in the correct direction, by the way. I don't know if it's reversed or not. So there's also a unit map, because it's an E-infinity ring, there's a unit map from the sphere into TMF. And this also hits quite a few classes. So you can really think about TMF as being a combination of the sphere spectrum and this ring of modular forms, hence topological modular forms. This kind of mixes these two things together. Okay. So
yes,
so there's
I have a question.
Yeah, sure.
Yeah, so you said that O top is a sheaf. So it's a functor from the category of Deligne-Mumford stacks? That's what...
Well, what was that, sorry?
So O top is a sheaf, right? So it's a functor from where to where? So what's the domain?
Yeah, no, I didn't actually write it down. So I guess, yeah, you could think about it as a functor from Deligne-Mumford stacks, which are étale over the moduli stack of elliptic curves. So i.e. I guess Deligne-Mumford site, étale site of ML. And yeah, it's a sheaf in this respect.
And then so this identity morphism, so you are taking as a mapping space or something, or just a morphism maps to an E-infinity ring?
You're just taking, I don't really understand the question, sorry.
So this TMF is an E-infinity ring. So this O top is a map from Deligne-Mumford stacks or this étale thing to the category of E-infinity ring spectra, right?
Yes, yep, it lands in E-infinity ring spectra.
So on that side, you take the morphism from, so you have this identity morphism, and then you just map it to the morphism space here, and then you get the E-infinity ring spectra on the
it's more, I think the formula up there is a little bit misleading, actually. I think you should write down a particular étale cover of the moduli stack of elliptic curves, and then define TMF as the correct sort of homotopy, the correct homotopy limit associated to this.
Ah, okay, just to, yeah, okay, thank you.
No problem. Okay.
Hey, Jack, quick question. Yeah. Does that spectral sequence always converge, or what are the restrictions there?
This is essentially like a Bausfield-Kahn spectral sequence associated to some, associated to what, Jack? Like a tower of spectra. So I think it converges a lot. It especially converges very well in this stage because it has a horizontal vanishing line. So it just converges for sure in this sense.
Cool, thanks.
But proving it has a horizontal vanishing line is kind of, I don't really understand. You have to read some things by Akil Matthew. Okay, so like I said, you could sort of think about TMF as some sort of universal elliptic cohomology theory. Not really though, because it's not an elliptic cohomology theory. It's glued to many things together. And there are actually theorems in the literature which prove things that we didn't know about the homotopy groups of spheres. For example, it finds new periodicity phenomena and stuff like this. So you often, to prove these theorems, you prove something in algebraic geometry, export this information through TMF, and then you obtain some homotopical information. But it would be nice if there was some sort of way of going backwards. If we could use sort of like atom spectral sequences and all this computational power we have in homotopy theory to somehow backtrack and sort of reverse manufacture statements in algebraic geometry that maybe we don't know or maybe are hard to prove. But it doesn't seem like we have a good idea on how to do this at the moment. And the ultimate goal of TMF, which we do not know how to do at the moment, is to understand what the cohomology classes are. So in particular, if you take, so for example, for complex K theory, the cohomology classes are virtual vector bundles. This is something very geometric, and this is where sort of like Adam's proof of vector fields on spheres uses this type of interpretation. But we don't have a geometric interpretation of TMF at the moment. There are some ideas by Siegel and Stolz and Teichner, but yeah, I also don't really know because it has to do with like field theories, and I don't know. I don't know too much about these things. But I don't really want to talk about that. I want to talk about a second construction of TMF. So what we did, or what the construction of OTOP allegedly does, is it first applies the Landweber exact functor theorem and then obstruction theory. But there's a different way to do it. What you could do is you could sort of embed your algebraic geometry inside spectral algebraic geometry, and then find some sort of moduli problem such that the solution to that moduli problem also gives you OTOP. This is kind of nice because you don't have to start with a homotopy commutative thing and prove that it is E infinity. You just start with something that is E infinity, but you have to prove something about it. It's kind of a different philosophy, a different sort of logic to approaching these problems. But as I want to get to later, it actually has some advantages. So let me take another quick drink now. My throat is getting dry. Okay, so yeah, let's talk about spectral algebraic geometry. Just not in a huge amount of detail, but I want to give you some intuition. And I've stolen all of these slogans from Lurie's book on spectral algebraic geometry, which it looks like a monster. And if you jump in at a random page, I think anyone is confused. But the introduction, for example, is quite nicely written. If you ever want an introduction to why you might be interested in spectral algebraic geometry, the introduction to this book is quite nice. So a slogan is that spectral algebraic geometry is just algebraic geometry, but you add E infinity rings. So rather than working over commutative rings, you work over these E infinity guys that we like to work with. Another interpretation is that you can just interpret the higher and lower homotopy groups of E infinity rings as somehow being extra information. So think about, you just have algebraic geometry, but spectral algebraic geometry somehow has extra information given by the higher and lower homotopy groups. So I'm going to give you a few examples that sort of demonstrate these two fake equalities that I've given you above, or sort of moral equalities. The first one is that there's a fully faithful embedding of infinity categories from commutative rings to E infinity rings, which sends a commutative ring to its Eilenberg-MacLane spectrum. So what this means is that anything you can do in commutative rings, you can also do in E infinity rings. In particular, if you know how to work with E infinity rings and you know their definition, then you're already doing affine spectral algebraic geometry. So if you've ever picked up chapter 7 of higher algebra, then you're already doing affine spectral algebraic geometry. And this also carries on to the functor of points perspective. So there's also a fully faithful embedding from the functor, sort of like from the functor category from classical algebraic geometry, functors from commutative rings to spaces, into the functor category now from E infinity rings to spaces. So so when we take up the functor of points perspective in spectral algebraic geometry, we're quite often looking at either the functor category on the right, or maybe we're only looking at functors from connective E-infinity rings. It depends what situation you're in. Another interesting point of view, which sort of alludes to the fact that spectral algebraic geometry is algebraic geometry plus extra information, is the fact that if you have an R module, if you have a discrete ring R and two discrete R modules, M and N, then you can take their discrete tensor product and you can take their discrete Hom module. And these are just, they are what they are. But you can also do this construction in the category of R module spectra, and you obtain R module spectra objects that have a lot more information. In particular, the homotopy groups of the smash product of R module spectra understand not just the discrete tensor product of R modules, but also all of the torsion. Furthermore, sort of like the internal Hom object doesn't just understand the Hom object from M to N, but it also understands all the higher X groups. So it's in this way that sort of spectral algebraic geometry and higher algebra actually understands all of the torsion and extension problems that occur in classical algebraic geometry. And I'll give you one more example of spectral algebraic geometry kind of in action, let's say. You can consider the sphere as some sort of nilpotent extension of the integers. And what do I mean by this? Is I mean that there's a map that goes from the sphere into the integers, which is just the truncation map as a map of E-infinity rings. And the kernel of this truncation map is exactly all of the elements in positive degree in the homotopy groups of spheres. And all of these elements are nilpotent by Nishida's theorem. So the fact that they're nilpotent means that the map of, let's say, yeah, the map of schemes from the spectrum of Z to the spectrum of the sphere spectrum is a homeomorphism, but there's lots of extra higher homotopical information going on the right. So it's somehow the spaces are the same, the structure sheaves are the same when considered as discrete E-infinity rings, but, well, sort of when truncating the thing on the right, but the thing on the right also has all of this extra higher homotopical information. This is what you think about as sort of an infinitesimal or some sort of nilpotent thickening. Yeah, I don't know, someone like Lars Hesselholt might say that sort of the higher homotopy groups of the sphere have something to do with the higher combinatorics of arithmetic.
Can you explain it a little bit more, please?
What was that? You're quite quiet.
Can you explain a little bit more? I didn't quite get the nilpotent elements there.
Okay. So you have this truncation map that goes from the sphere into the integers, and this just sends, it's the identity on pi0, and it kills all of the higher homotopy groups of spheres. Well, it sends all of those guys to 0. And all of those elements in the positive homotopy groups of spheres are all nilpotent elements. And this means that, yeah, so in particular, if you look at this map of Zariski spectra, I mean, the Zariski spectrum is defined by the prime ideals of a particular ring. And if you divide out a ring by a nilpotent ideal, then the quotient ring is going to have the same prime ideals. So this is why it's a homeomorphism on spectra, but the higher structure sheaves the structure sheaves contain different information. Yeah, sorry, I can give a more detailed example later, perhaps. Okay, so now we get into the definition of a derived stack. And the definition is going to follow exactly the definition of a regular stack, except we replace commutative rings with E-infinity rings. So I'm going to say a derived stack is just simply a functor from E-infinity rings to spaces, which is also an étale sheaf. So it still has this sheaf property that I asked regular stacks to satisfy. And you might not be surprised, but there is a derived moduli stack of elliptic curves. And this is defined by sending a ring R. Well, you first need to come up with a notion of what is a derived elliptic curve over an E-infinity ring, but this has been done by Lurie. And you then define this moduli stack by sending an E-infinity ring R to the infinity groupoid of derived elliptic curves over this E-infinity ring R. Now, what you can do is you can ask, well, not what you can do, but here's a definition. You say that an elliptic curve over an E-infinity ring R is oriented if it orients in the sense that there is some sort of orientation somewhere, which forces the E-infinity ring to locally look like it comes from the Landweber exact functor theorem. So in other words, if you have an elliptic curve and you have an orientation of that derived elliptic curve over the E-infinity ring, it means that E-infinity ring looks like it came from the Landweber exact functor theorem. And you can also define a derived moduli stack of oriented elliptic curves in exactly the same way. You now have a definition of what oriented derived elliptic curve is, and you just define this moduli stack to send R to the infinity groupoid of oriented derived elliptic curves. Okay, so I've brought up a few of these things, but they come together on the next slide. Take another quick drink.
Yeah, so this oriented definition has nothing to do with E?
It does have something to do with E, but it's very hidden. So the orientation that comes with, like, an elliptic curve is oriented if it has an orientation, which is very much related to the elliptic curve.
Okay.
Yeah, sorry. If you read through Elliptic Cohomology 2 by Lurie, there's all the definitions in there.
I think it's a typo in the slide, probably.
Oh, what was that?
Is there because there's a typo in the slides?
Yeah, it's a very technical sort of thing, and it will move us in a strange direction. Okay, so what can we do with all of this information? I've just defined two derived.
Is there like a notion of, I don't understand what an orientation is, but I know what a framing is. Like, could you like use it to like say what a framing, like?
It's something very specific that I think was explicitly built to essentially say that your elliptic curve over your E-infinity ring, it forces the E-infinity ring to be complex oriented and forces the formal group of that it forces the equivalent formal group of that complex oriented E-infinity ring to look just like the elliptic curve. That's what the orientation does. Yeah.
Oh, thank you.
So you can use all of this stuff to define TMF now. And how do you do that? Well, you just consider these moduli stacks now as moduli stacks. We like derived moduli stacks. And there are two maps that go between these moduli stacks. The first one, the one on the left, is a forgetful map. So what it does is it sends an elliptic curve with an orientation over an E-infinity ring R, just to that elliptic curve over the E-infinity ring R. It just totally forgets about the orientation. There's also an infinitesimal thickening, which goes from the classical moduli stack of elliptic curves into the derived moduli stack of elliptic curves. This is, and this map is very, very similar to the map from the spectrum of the integers to the spectrum of the sphere spectrum. Sorry, I didn't choose these adjectives or nouns. So once we have these two maps, you can do something. You can take the structure sheaf of the thing on the left and you can push it along the forgetful map, and then you can pull it back along this infinitesimal thickening. And it turns out that this object is exactly O top. It turns out that you've exactly reconstructed O top just in these two slides. So in other words, O top is actually a sheaf that comes from a moduli problem in spectral algebraic geometry. It's not just something that you can apply Gauss-Hopkins obstruction theory to once you've applied the Landweber exact functor theorem. It's something that naturally lives as a solution to a moduli problem in spectral algebraic geometry. And something that I only sort of realized recently is that, I mean, the definition of this sheaf by sort of, you have a structure sheaf and you push forward and then pull back. Of course, the definition is very easy, but it's also somewhat intuitive because an orientation of elliptic curve is forcing the E-infinity ring to look like it came from Landweber exact functor theorem. You're sort of almost forcing things to fall into place, but phrasing it in terms of spectral algebraic geometry. So I claim that constructing this sheaf is actually easier than constructing O top the classical way, But of course, you need to have a little bit of spectral algebraic geometry already in your pocket.
Did you say that O or L is the structure sheaf of the moduli stack of oriented elliptic curves?
Yes, that is what I said. Yeah,
Okay,
exactly. Okay, so this is great. And of course, I don't want to lie too much. I mean, there is a big paper by Lurie where he proves this, and it is very hard to prove the equivalence between OTOP and this pull-push of the structure sheaf. It's very hard to prove this equivalence, but I mean, once you've proven this equivalence, then you can forget about the definition on the left and you can work with the thing on the right. So in conclusion, you can define TMF by just taking the global sections of this new guy. So again, TMF comes from a structure sheaf from spectral algebraic geometry. Okay, are there any more questions at this stage?
I have one about what he said in the last slide. So like,
yeah.
Maybe you can ask this afterwards, but I'm kind of wondering what the relation between like so like where he says in like elliptical homology theory that like an orientation of like an elliptical homology theory is just like is just a an elliptic curve that whose formal neighborhood is the one that's given by the cohomology theory.
Yep, this is so in elliptic homology 3, Lurie gives 2 or 3 definitions of an orientation and shows that they're all equivalent. There's also a definition given in elliptic homology 2, but yeah, they're all equivalent. They're all quite nice. But yeah, it's exactly what you're thinking.
Like, oh yeah, so I guess maybe I should look over there, but like, I don't know if it has any relation to like what we think about as orientations in topology.
I mean, I think it's not unrelated, but I don't know off the top of my head what the relation to like a BU orientation or something like this would be. I'm not quite sure. But we could talk about that more after, maybe.
Yeah, thank you.
Okay, so I've got a few more minutes, and I'd like to talk a bit more about things from spectral algebraic geometry, because not just TMF can be recovered in this way. So I'm going to fly through some slides here. I'll give the slides to Sarah so she can put them up, and there'll also be some references at the back, so don't worry about taking notes. I just want to show you that there do exist some things in spectral algebraic geometry that give us more than just TMF. So there's a sheaf, which I'm just going to call OTOP BT when I say it out loud. And it comes from another collection of spectral moduli stacks. You can define an object called a p-divisible group. And once you define what a p-divisible group is over an infinity ring, you can look at the 3 moduli stacks that we saw before. You can look at a classical moduli stack, a derived moduli stack, and a derived moduli stack of oriented things. Excuse me, I'm getting a bit excited. And in the same case as for elliptic curves, you can consider maps between these things. You have the moduli stack of oriented p-divisible groups, a moduli stack of derived p-divisible groups, and a moduli stack of classical p-divisible groups. And you have a forgetful map on the left, and you have a sort of infinitesimal thickening on the right. Cool. And now you can define your sheaf OTOP BT exactly the same way that Lurie proved, well, in exactly the same way that we constructed OTOP. You can define OTOP BT by just, again, looking at the structure sheaf of the thing on the left, first pushing along the forgetful map, and then pulling back along this infinitesimal thickening. Okay, so you've defined this sheaf, and again, I'll ask one last time, what's the point of doing something if there's not a bunch of examples that you want to apply it to? But there are a bunch, oh, sorry, before examples, there's a theorem. So, there's a theorem by Lurie that says that this sheaf, OTOP, behaves exactly the same as the Landweber exact functor theorem. So it says that you can define OTOP in such a way that it outputs infinity rings, which, again, look exactly like they came from the Landweber exact functor theorem. I don't think this theorem of Lurie is something I want to hop on too much right now. But like I said, what's the point of constructing this OTOP BT? It's because we have a bunch of examples in mind. I maybe was a bit bold in saying everything comes from it, but for example, you can write down this formula that I've given there, and that gives you a p-divisible group. Now, I haven't told you what a p-divisible group is, but that's fine. But it's a very simple formula. It's just the spectrum. You're sort of taking the integers and you're attaching p to the rth roots of unity. And you can now, the collection of the sort of inductive collection of all these schemes is called mu p infinity. And this is a p-divisible group. And you can take O top bt of this p-divisible group, and this gives you complex K theory. So this is something that's pretty cool. So complex K theory also comes from this spectral algebrogeometric point of view. If you have an elliptic curve, you can consider, well, an elliptic curve is a group scheme. So in particular, it's a group. So in particular, you can look at the p torsion, and its collection of p torsion called EP infinity is also a p-divisible group, whatever these objects are. And you can also take O top bt of this p-divisible group, and this gives you TMF. Again, there are some p completions and there are a few extra details that, well, there's many details that I'm sweeping away here, but the thing I want you to come away with is that there are more constructions that give you more E infinity rings that you're comfortable with. Another example for all the chromatic homotopy theorists in the group is Lubin-Tate theory. So if you have a perfect field and a formal group of height n over that perfect field, then you can associate to it a formal group, a p-divisible group. And Lubin-Tate theory then gives you a map from these Witt vectors and these power series into the moduli stack of p-divisible groups. And you can take O top of this. You can take O top of BT of this guy, and that gives you exactly Lubin-Tate theory or Morava E theory. Now this example, I mean, you could give a whole lecture on this example. It's very beautiful. But essentially, this example comes from being very clever in choosing how to construct your p-divisible groups. But in general, if you have some fancy way to construct p-divisible groups, to find Deligne-Mumford stacks which come with p-divisible groups, then you can just apply O top BT to this, and you can see what E infinity rings come out. And this is exactly what Behrens and Lawson did, and this is how they defined topological automorphic forms. And in fact, there's no other way to define TAF other than to use this sheaf. You can't construct it using Gauss-Hopkins or I mean, you probably could, but no one has. This is the only way at the moment to construct things like TAF. And there's one other thing I want to mention, and that I'd like you to take away. And that's the fact that sheaves are functorial by definition. By nature, they are a functor. So in particular, if we have some automorphism of an object, then this is going to induce a map on the, it's going to induce a map on sections. So in particular, you can construct automorphisms of all the examples I've given you and see if you obtain maps of E infinity rings, like you might obtain endomorphisms of complex K theory, or endomorphisms of TMF, endomorphisms of Lubin-Tate theory. And it turns out that you can construct cool things. You can construct Adams operations, for example, by looking at the effect of, by looking at the effect on maps that you construct by hand on p-divisible groups and then taking O top BT of this map. And you can also construct Adams operations for TMF. You can also construct many more operations for TMF. And the reason why I'm running out of breath is because I'm very excited, and because this is kind of what I'm doing in my PhD project. So in conclusion, I sound like I'm giving a book report when I say that. In conclusion, I hope you got away with this, realizing that the algebrogeometric point of view of homotopy theory not only shows us about, it not only tells us about things that we already know, but it also tells us new points. It tells us new things, gives us a new point of view. And spectral algebraic geometry sort of strengthens this point of view by combining homotopy theory and algebraic geometry in a natural way. So it adds a lot of functorality and naturality to our proofs and constructions. And in particular, if you take that spectral algebrogeometric point of view when constructing TMF and O top, the proofs are very robust. So in particular, when you construct a sheaf by pulling and pushing along explicit maps of stacks, that is a sheaf, and there's no question about it. But if you want to use Landgraf-Exact-Functor theorem and then apply Gauss-Hopkins obstruction theory, that might be fine. You might obtain an E-infinity ring, but then you need to do Gauss-Hopkins obstruction theory again with respect to maps. And all of a sudden, there's questions about functorality and lots of complications. And so when you do things with spectral algebraic geometry, these sorts of complications go away, as long as you are willing to deal with slightly more generality. Anyway, that's all I have to say for today. And here's a list of references if you want to look anything up.
Yeah, for everyone. Thanks, Jack. Are there further questions?
Thank you for the clap.
Yeah, so this topological automorphic forms, you said that, so on this Pi2, they give the automorphic forms, that's why it's the name, or?
I'm sorry,
model forms?
I'm finding it
quite
hard
so
to
for the topological, for the topological automorphic forms, so on the Pi2, you get the automorphic forms, the classical automorphic, or why the name? Just
well, yeah, good question. So the reason why, well, actually no, I get a little bit confused why it's called topological automorphic forms. Yeah, I'm gonna have to refer you to the book of Behrens and Lawson called Topological Automorphic.
Okay.
I know how to define the Deligne-Mumford stacks that they construct, but I find a lot of the rest of it very mysterious.
Okay, thanks.
Sorry about that.
No.
Any other questions for the recorded portion of the talk?